Okay, question 3, quite a long question, so bear with me on this one. So we've got a solution of iron 2 and iron 3. It's a mixture. And the first thing they did was titrate with manganate. Manganate's an oxidizing agent, so that's turning all my iron 2 to iron 3. So that's a standard way to determine how much iron 2 is present in solution. Then we're doing some weird stuff like a back titration where we're taking, because we don't know how much iron 3 there is, what they're doing is taking the nickel and reducing the iron 3 to iron 2 so that all of the solution becomes iron 2. And then we can work out how much that is. And basically, if we know the amount of Fe2 plus that was there at the start, and then the second titration, so the first titration is giving us just Fe2 plus, just the number of moles, and then the second titration is giving us Fe2 plus plus Fe3 plus, and from that we can therefore work out a difference, and it wants to work out the iron 2 and the iron 3 concentrations. So it's a bit like one of those equilibrium questions really. You've got one mole and you can one of the moles, and then you know what it changes to, so you can then work out what the other one is by difference. Okay, but let's actually get to, I've underlined, highlighted any of the kind of important numbers. Let's actually get to electropotentials and what the question's asking first of all. So these are the bits we actually need to answer. Show that the reduction of iron 3 to iron 2 is likely to proceed to completion without significant further reduction of iron 2 to iron. So what I'd be doing there is I'd be having a look and working out some E cell values. So if I was to look at what's happening, so nickel, if I look at this, that's one of my cells. We've got Fe3 plus plus an electron going to Fe2 plus, that's another thing, and I've got Fe2 plus could in theory gain electrons to form Fe. Now in fact the nickel electrode is more negative than both of these. Is more negative than this one, but not more negative than this one. And in fact I can also work out an E cell. So if I wanted my nickel to lose and my iron 3 plus to gain, so that I had this reaction happening, then, oops, my bad, nickel plus 2 iron 3 plus goes to everything. The E cell value for that is plus 1.02 volts, so that's definitely spontaneous and it goes to completion. If I were to compare that with adding it to my iron 2 plus and making Ni2 plus and Fe, that cell potential actually works out as minus 0.19 volts. So this one is more negative than that one, so that reaction would not be spontaneous. So we can assume that there wouldn't be any further reaction of my nickel. So all the nickel's going to do is turn Fe3 plus to Fe2 plus. It's going to stop there. That means that all of my iron in solution is now in a form that I can titrate to. Okay, why it was necessary to remove excess nickel, guess what? It's probably going to be to do with electropotentials. It's a suggest, but to be honest, we could work it out anyway. We have manganate, which is a very strong oxidizing agent present here. Necessary to remove excess nickel. Well, nickel could easily turn into nickel 2 plus, because we've established that this is quite a negative electropotential. The manganate potential is plus 1.5. Nickel would be extremely readily oxidized, so that would mess up my titration value. But the other thing that would happen is we've just decided that this reaction is spontaneous. So nickel plus 2Fe3 plus goes to 2Fe2 plus 1 volt, that is spontaneous. Here, during the titration, Fe2 plus reacts with MnO4 minus to make Fe3 plus. So I could be making that, if I had nickel left in the mixture, then that Fe3 plus could then react with the nickel and form Fe2 plus. And I just get one of those never-ending manganate titrations, which, let's be honest, we've had one of those never-ending manganate titrations where we never, ever reach the end point. So both of them would give you a titer value much larger than what we'd expect. We've all been there emptying our burette of manganate and not getting anything out. Okay, so here's the real beefy question. Here's the calculation part. Use the data given to determine the concentrations of the iron 2 and the iron 3. So the iron 2 part is easy peasy. It's a standard titration question. I'm just going to work out. So for my Fe2 plus, what I'm going to do, I'm going to work out my moles of manganate, which is there. I've got my 21.60 over 1,000 times 0.021, and that gives me 4.536 times 10 to the minus 4. Then I'm going to convert that into my moles of Fe. It's a 1:5 ratio, so my moles of Fe2 plus is therefore going to be 2.268 times 10 to the minus 3. So I've just taken that value, times it by 5. Okay, so the concentration I could work out straight away because I actually know that that's the moles of Fe2 plus in 25 centimetre cubed. So I can divide it by 0.025, and then my answer for concentration of Fe2 plus is going to be 0.0957 moles per dm cubed. So that bit's easy to do because Fe2 plus is always really easy to find with manganate. Okay, the Fe3 plus part is just done by difference. So what the nickel's done is turned all my Fe2 into all my Fe3 into Fe2, so everything is Fe2 plus now. So obviously my titer value is larger, so I'm expecting a larger. So my second titration, I'm going to do the same thing. I'm going to work out my moles of manganate. This time it's 44.4 over 1,000 times by 0.02 10, and my moles of manganate there is 9.324 times 10 to the minus 4. Same thing again, times it by 5 to get my moles of Fe2 plus that are in this mixture, and it's 4.662 times 10 to the minus 3. Now what that equals is my Fe2 plus plus my Fe3 plus. And I know from my previous question that in the same volume, my 25 centimetre cube, my moles of Fe2 plus before I did all my conversion of Fe3 was 2.268 times 10 to the minus 3. So what I'm going to do is take away 2.268 times 10 to the minus 3, and that's going to give me 2.394 times 10 to the minus 3 moles. That is my moles of Fe3 plus. That's not my concentration though, so again, same thing, it's in the same volume, divide it by 0.025, and that gives me 0.0957 moles per dm cubed.